Problem number 3108, minimum cost walk in weighted graph. There is an undirected weighted graph with n vertices labeled from 0 to n minus 1. You are given the integer n and an array edges, where edges I equals ui, vi, wi, indicates that there is an edge between vertices ui and vi with a weight of wi. A walk on a graph is a sequence of vertices and edges. The walk starts and ends with the vertex, and each edge connects the vertex that comes before it and the vertex that comes after it. It's important to note that a walk may visit the same edge or vertex more than once. The cost of a walk starting at node U and ending at node V is defined as the bitwise end of the weights of the edges traversed during the walk. In other words, if the sequence of edge weights encountered during the walk is W0, W1, W2 to Wk, then the cost is calculated as W0 bitwise W, bitwise and W1, blah blah, where and denotes the bitwise and operator. The cost of a weight starting and weight is defined as the bitwise and of the weights. Okay. You are also given a 2D array query, where query I equals SITI. For each query, you need to find the minimum cost of the walk, starting at vertex SI and ending at vertex TI. If there exists no such walk, the answer is -1. Return the array answer, where answer I denotes the minimum cost of a walk of query I. Okay, so it says the walk may visit the same edge or vertex more than once. The weight is it all positive integers? It's edge I, W. Yes, it is all positive integers. Okay, so then we will not, we will avoid walking the same edge, because then it is gonna cost more. Okay. So example 1, it has edge 0, 1, 1, 3, 1, 2. Okay, the first thing that I would like to do is I think I will use DFS because we are calculating the minimum cost. And I'm selecting between BFS and DSU, but I think DFS will be much better. Because there is weight, and So if we use the FS, then we need to first build the graph. So build a graph, it will be like and multiply by n graph, and graph ij will be the weight between vertex I and vertex j. And after building the graph, so the AND operator is okay, so when and we are going to traverse each query okay, so for after building the graph, we will for loop the query and traverse the graph starting from query the start, and we should using this to starting point and ending point. So if it's like for DFS we will have the visited set. So and for each query we will reset the visited set, and so it will be if reach ending vertex, then it's kind of like finding every possibilities path between two vertex, and so if reach ending vertex, then we will return the cost, else we will try to find other possibilities that does not visit it before. Okay, so we will have, we'll first build the graph. We'll have a graph that will be zero at first, and then we have and for loop. So for edges, for U, V, W, and edges, and graph, you will have graph UV will have W, and graph VU will have W as well, since it is an undirected graph. Okay, then we will have our DFS, and we will have our visited stack. We'll reset every time for each query. So we will have we'll for loop the query start and T in query, and the set will be reset, and we will run DFS as with T. Okay, so I and J, and we will have the minimum cost, like this is global, so I'll have if, and then we'll have a local, like for every visit, for every query we have its cost. We have we can use answer I. We can have answer, so it's answer with the length of queries. We'll first have inf, and then we'll have local, here we'll have min cost for every possible path, so it's inf as well, and after every DFS we will have, we will add I think we can use answer and we don't need this. And if answer okay, well, we need query. This will be I, and then we'll have the start and target point. If we want to access, I think, okay, Yeah, I think we'll have a local, then we don't need to pass the I inside. Yeah, so we'll have a min cost for every DFS traverse, and so after DFS, if min cost is smaller than nth, then we will update answer I equals min cost, and then we'll return answer. Yes, and then the DFS would be, so basically the time complexity will be, for building the graph it's ON, and then OE is the edge, and we will loop through the query, so we will have Q, and for each DFS we'll walk through the possible path between S and T. I think it will be totally we have E number of edges, and we have N nodes, so it's like I think it will be 2 with the power of n plus e. Yeah, I know it will. Yeah, it will time out, but let's first use the brute force and then see where to improve. Okay, so for DFS, now we will add it to the visitor set. And if I equals j, we need non-local in cost. And if I equals j, that means we have finished the walk, so we will have I think we need to we need mean cost and cost. So if I equals j, then we will have mean cost equals min cost with cost. Otherwise, we will have we will loop through its connected nodes. It will be for loop nodes in graph I. if node we need enumerate node and weight if node is not any visited and weight is larger than 0. Okay, we have weight equals 0. Yes, okay, so we should have -1. Yeah, and we will run DFS I with J. Oh, sorry, node. And yeah, we have to calculate the cost. So the cost will be cost and equal to its weight, and its weight will be and we'll do it here. Cost be the weight J. Weight. Yeah. And after we have to, yeah, I'm thinking how to remove back to the before. I think we'll okay, maybe like if cost equals 2 then weight is 3, and if they have and, it would be 2 and 3 equals 10. 2. So I'm thinking, yeah, it's I think I need another example, like cost equals okay, so if cost is 4 and weight is 2, then 2 with 4 will be 0. So how can I get back to 4? So now cost is 0. Weight is 2. I need to get back to cost equals 4. I don't think it's possible. Yeah, but I need a way to maybe or I should, yeah, if then it's cost, then I should put cost in the parameter, so it would be like cost and yeah, it would be cost and weight yeah. So then this we should default to 1. Yeah, since everything bitwise and with 1 is itself. Oh no. I think should be not 1, but yeah, every bit should be 1. And I think so for 10 with the largest weight will be 10 with the power of 5, and for that okay, I need a number that every bit, like to do every bit is 1. Okay, so we can try run yeah, we can maybe use this. So for example one, our graph will be, let's see, it's yeah, graph 0 will have it have 5 nodes, so it will be, okay, it's like this. And for the 0 node, it will be 7. This will be 7. And 1, 3. So 1. This will be 7. This will be 7. And 1, 2, 1. So 1 will be 1. Wait, for each node itself, the node itself, or maybe we can use a default dictionary, so yeah, we don't need to, it's like an n time complexity. Yeah, we can have a default dictionary, I think, build a graph, and graph, yeah, and it will be, yeah, key will be the vertex, and value will be a list of connected vertices, and weight. So yeah, we will change this to a default div with empty list as default, and yeah, for graph U, we will append V. We'll have a tuple with V weight, and append U with, yeah, weight. Okay, so we will have, yeah, for example 1, we will have 0, 1, 7, and 1 will have 0, 7. Okay, 1 will have 3, 7, and 3 will have 1, 7. Okay, 1 will have 2, 1, and 2 will have 2 will have 1, 1. Okay, we have to change this to graph I. Yeah, we will have node and weight. Okay, so then we will start it here for query. Query will be 0 and 3, so it's I is okay. It's 0 with 0 3. Okay, so we will start with 0 3 and magic number. So we will add 0 to the visitor set, and if 0 equals 3, no, so we'll not go into this condition. We will start our for loop. Graph 0 is 1 7. So if 1 is not in the visitor set and 7 is larger than 0. Okay, I think we don't need this. Yes, so not in visit. And then we will run DFS 1 with 3 and cost, and the magic number with 7. So we will add 1 into the visitor set. 1 is not equal to 3, so we will have we will have 1 now, and we'll have node 0. Since node 0 is already in the visit set, so we will not run. We will have 3 7. 3 is not in the visit set. Okay, run. So we'll have 3. And weight will be 7 and 7. Okay, the current cost is a magic number, as have magic with 7 and 7, and it's already 3, so yeah, it's equal to J, so we will have this added to compare with the min cost. Oh, and we need return. Okay, and then we will have so it's 7. Okay, so min cost now is 7, and then we will be back to 1, and there is 2 1. Okay, node is 2, node is not in the visited set. Oh, so we need we also need to remove the visitor set. Wait, I think maybe because it is an AND, a bitwise AND operator, it's not sum, so maybe like I mean, because you can go to you can visit the same edge or vertex more than once. I think if you want to minimize the cost, yeah, the best thing is to have 0, then you will have the minimum. So okay, I see. Yeah, it's I think some of the feature of like properties or feature of an operator I am not really familiar, like I missed something, so yeah, if I'm thinking if a group of nodes that they can form a connected component, then if this connected component contains the starting vertex and ending vertex, then we can find the we can bitwise all the edges or pick. We need to pick. So the problem is how to make the minimum for a group of integers with bitwise end. I think I want to check the solution. Oh. Okay, so there is like bitwise and if you bitwise add more numbers, then you'll get smaller results. Okay, cool. Then like just that, like I said, we can find a connected component, and bitwise all the numbers in a connected component, and we got the minimum. And if both vertex is not in the same connected component, then we will have -1. Okay, so then will find the connected components starting from queries S and yeah. So traverse every, and we will not return. Yeah, I think if visited said yeah, we will have all the we don't need minimum, like cost will be yeah, I think we will have cost equals weight. We don't need a parameter, and we will have non-local cost. Cost will be the magic number. If visit, if t not in visited, then we will, if t in visited, and we will have answer I equals cost. Don't need this. We don't need j. Yeah. Add I with weight, cost plus weight, plus node. Yeah. Okay, so then let's start again. Okay, so first of all, visit set will be added 0, and we will have 1 7. 1 7 is 1 is not in the visited set, so we will add the weight to the cost. So it is magic. Yeah, maybe we can set it to the weight of S. Well, but we don't know. The magic number was 7, and then we will have DFS node 1, and for 1 we will yeah, it's 0 7. Since 0 is already visited, we will continue to 3, node 3, and it will be weight 7, and we will have DFS 3. We'll add it to 3 added to the visit set, and it will be 1 7. 1 is already visited, so we will return, and we will move on to 2 1. And 2 is not in the visited set, so we will have, oh yeah, it's 1, and we'll add it to the visited set. 2 will have 1 1, and 1 is already visited, so we'll return and return. Okay, so back to here, and if t is 3, 3 is in visit, so we will have answer I to the cost. Yeah, and the next one will be, okay, it's 1 with 3 4. Okay, so we'll start with, we should reset. DFS 3, we'll add it to the visit set. For 3 will have 1 7. 1 is not visited, and we will have its cost 7. We'll visit node 1. For node 1, we add it to the visit set, and then 1 we have 0 7. 0 is not visited, so we will have its weight 7 and visit 0. And for 0 we have 1 7. Since 1 7 is already visited, we'll return, and it's continue to 3, node 3. Node 3 is already visited, and we'll continue to 2. Okay, so we'll have 2, and we'll have its weight 1, and we'll visit DFS node 2. Yeah, and for 2 it's 1 1, and 1 is already visited, so we'll return. Okay, then we have this cost. Since t is 4. Okay, 4 is not in the visit set, so we'll have -1. Yeah, we will not run this condition. Okay, so it's correct, and we need to find out this cost. Does it have it in? Yeah, if every bit is 1, then we should have like yeah, it's like 2 with the power of like 2 with the power of 5 plus 2 with the power of okay, I think this magic number will be difficult to calculate, since yeah, like it will be like the yeah, it will be the power 2 with the power of n minus 1 should be larger than the limitation 10 with the power of 5. And that n is, I think that's not easy, or it might be too large. Or maybe we can try. So yeah, then we will have this plus 1, and we will have log. Right. This will be log 2, and will be this, and yeah, it would be 2 with the power of this thing, and minus 1. Let's have integers. Oh, it's 0. Or we can just collect all the costs and all the weight, and then we will do the bitwise. So I think we will have weights. So don't need cause, but we need, we will add a weight. And for every t in the visit set, we will do the bitwise calculation. So use -1. Okay, it says we can use -1. Let's try. If we have caused -1. I found out why this is error, since the solution said you have to the minimum, the best solution, to find the minimum cost, the best way is to go through every edge, not every node. So I misunderstanding to every node. So this is, I think we should put it here. And there is a new idea that I have never learned before, is that in Python the default value of bitwise AND can be set to -1, since -1 in the bitwise is all 1, so it can have -1 as default. I have calculated time complexity, and it's EOE. E will be the length of the edges for this creating the graph. And then for each DFS we will have n plus e. N is a node count, and the edges. We will traverse the whole graph, and not the whole graph, but for DFS we will walk through the connected components started from query S, and calculate the end value for every edge. So it's the time complexity of DFS will be n plus 1, and since every query we will do it again, so it's q multiplied by n plus e. Okay, so the bottleneck will be here. Since q is query length is 10 with the power of 5, and if it multiplied with n is 10 with the power of 5, then it's 10 with the power of 10. It's gonna so I think we should optimize here because the bottleneck is here, and because every time we have a new query, we will do the traverse again. And what about there, like all the nodes are in the same connected component. So I think we have to, I have read the solution, and I think we have to memorize which node, which node belongs to the same connected component, and the end value and we need to keep track of every end value for each connected component. So we will have the connected component ID, and it will be, we'll start it from -1 with the length of n, since every node has its connected component to be long. And we need connected component value. It's the AND. Okay, we'll have AND, and it will be empty array. Yeah, like we will use this ID to query the AND value of the component. Okay. And okay, so for each query, I think it will be, if S starting node and its ID, we will query its if CC ID if both of the two nodes are in the same component, then I think we should for we will first calculate. We'll first finish all these value, and then we will for loop the query. So and we will have the visited set. I think will be here. Don't need this. Maybe later on. So for I in range n, if I not in visited, then we will run DFS I. And we will have cost. Pick one. Yeah, for like started from 0, we will calculate its its connected component, and we will calculate the cost as well. So CC we will change the connected component ID for each node that we pass through. So CC ID I will be length of CCN. Okay, and for CCN, okay, so cost, so after the DFS we will have the total cost, and we will add think we will just append. Yeah. Then we will finish this these two values, and then we can query in the queries. So okay, we have if S belongs to the connected component, and the connected component we will check as the connected component that S belongs to and also T belongs to. If they are the same, then we can check its and answer I will be the end value of else if they are not the same, then it's going to be -1. Yeah, so that's it. Okay, it's passed.